Some of the components of a simple personal computer is given here. We have central processing unit placed on the main board of the computer and also main memory elements placed on it. For the monitor, which is the basic output device of a personal computer, we have video controller. And for the keyboard, which is the basic input device for the computer, we have keyboard controller. We have USB controller to which, for example, a printer can be connected. And also we have hard disk controller for controlling the hard disk device. The memory on the main board is called the primary memory or the main memory. Hard disk is called the secondary memory. We have different processor architectures. For example, it may be a pipeline architecture, superscalar architecture, or multi-threading, hyper-threading architecture, or multi-core architecture. All these different architectures have implications and complications on the operating system. In a three-stage pipeline, this is a simpler architecture compared to the superscalar CPU. We have fetch unit, decode unit, and execute unit. Fetch unit fetches instruction from the main memory. Decode unit decodes it and understands what is to be executed. And execute unit executes the instruction. In a three-stage pipeline, when the executing unit is executing a decoded instruction, meanwhile, the decode unit may be decoding the next instruction and fetch unit is fetching the next instruction to be decoded. However, if a superscalar CPU architecture is considered, there may be more than one fetch unit connected with decode units. And then there is a holding buffer in which decoded instructions stored, and there may be more than one execute unit which are executing different instructions decoded here in parallel. In this figure, a quad-core chip with a shared L2 cache memory is shown. Each core has a corresponding L1 cache and there is a common L2 cache. Each gets instruction from the common L2 cache area. In this configuration, we have a quad-core chip with separate L2 caches in addition to the separate L1 caches. Ideally, memory should be extremely fast, abundantly large, and very cheap. However, if the access time is shorter, that is, when the memory is fast, it becomes more expensive. Therefore, the size of that memory in the computer is restricted. A typical memory hierarchy is given in this figure. The numbers are very rough approximations. If we consider registers, typical access time is 1 nanosecond and typical capacity is less than 1 kilobyte. And there is cache, typical access time is 2 nanosecond and typical capacity is 4 megabyte. The main memory has typical access time 10 nanosecond and typical capacity 1 to 8 gigabyte. A magnetic disk, this is hard disk, has a typical access time 10 millisecond and typical capacity is 1 to 4 terabyte. Whenever a resource can be divided into pieces, some of which are used much more heavily than others. Caching is often used to improve performance. A caching system has the following issues to be solved: when to put a new item into the cache, which cache line to put the new item in, which item to remove from the cache when a slot is needed, where to put a newly evicted item in the larger memory. L1 cache is always inside the CPU and usually fits decoded instructions into the CPU's execution engine. Typically, it is 16 kilobyte. L2 cache holds several megabytes of recently used memory words. L1 cache should not have delay. However, L2 cache may have delay of 1 or 2 clock cycles. The storage types, while RAM, ROM, EEPROM are types of main memory, flash memory and magnetic hard disk are the types of the secondary memory. In this figure, structure of a disk drive is given. In a hard disk, we have several plates, and on each plate we have two surfaces, and for each surface we have a read-write head. And as the arm moves, the head is placed on different tracks on the surface. Each head is in the same track. Each plate in the hard disk is connected to the rod at the center. The rod is turning. Because of that, when the head is at a point, whatever the sector, just below it is read or written. All the heads are on the same sector and same track of the different plates. The steps in starting an I/O device and getting interrupt is explained in this figure. When the CPU needs to get information from an input-output device, for example from disk, then it sends the requirement to the disk controller while CPU is doing some other operation. In parallel, the disk controller gets information from the disk drive, and when it is completed, it informs the interrupt controller, which interrupts the CPU and load the information collected from the disk drive into the CPU. While the current instruction is executed, if it is needed some I/O operation, then interrupt processing is done. Interrupt processing involves taking the interrupt, running the interrupt handler, and after that code is executed, it involves returning to the user program through the next instruction. In this figure, the structure of a large family of mainboard containing x86 processors is given. This is the family of the processors similar to 86. We may have more than one processor, each having on L1 cache and also a shared L2 cache. Furthermore, GPU cores for the graphic operations and memory controller to access the main memory. The information between the memory and the memory controller is through a bus. There may be several memory units connected to the memory controller. Through the desktop management interface, it is connected to the platform controller hub, which has buses to the PCI slots, and each slot a different card may be inserted. And also we have buses connected to hard disk, USB ports, and to Internet. USB stands for Universal Serial Bus. In the operating system zoo, we have different kind of operating systems. Each kind of operating system is developed according to the requirement of the related system to be developed. For example, mainframe operating systems, server operating systems, multiprocessor operating systems, personal computer operating systems, handheld computer operating systems, embedded operating systems, sensor node operating systems, real-time operating systems, smart card operating systems. Process is a key concept in all operating systems. A process is defined as a program in execution. A process is associated with an address space where the program is loaded and also associated with a set of resources which are used by the program. Processes can be thought of as a container, holds all information needed to run program. Here an example of a process tree is shown. Process A created two child processes which are B and C, and then process B created three child processes which are D, E, and F. Here is a file system for a university department. In the root directory, we have two files which are students and faculty. For the student file, we have a record for each student, Robert, Matthew, Leo, for example. And for the faculty, we have a record for each professor. Professor Brown, Professor Green, and Professor White. Each professor may be teaching several courses. Those information is a part of the courses. And papers and also grants. These are files. And also a professor may be a member of a committee. And there may be different committees. All of this information stored in the secondary storage is corresponding to a file system for a university department. In Unix, we have mount operation for the devices. Before mounting, the files on the CD-ROM are not accessible. After mounting, they are part of the file hierarchy. Here, CD-ROM is connected to the file hierarchy of the Unix system. This is the figure after mounting the CD-ROM to the file system of the related computer. Pipe is another concept in the Unix system. Pipe is another concept in the Unix system. It is a sort of pseudo file that can be used to connect two processes. Communication between processes in Unix looks very much like ordinary file reads and writes. In this figure, two processes communicating a pipe is shown. Each process is sending information to the other one through the pipe. These are imaginary files, not in real. An analogy may be constructed between the development of an embryo and development of a computer. Development of an embryo, which is called ontogeny, repeats, that is, recapitulates the evolution of the species, which is called phylogeny. After fertilization, a human egg goes through many simpler forms before turning into a full-functioning human baby. Each new species of computer, which may be mainframe, and then mini-computer, personal computer, handheld computer, and embedded computer, smart card, etc., goes through the same development as its ancestors did, both in hardware and in software. A change in technology renders some idea obsolete and it quickly vanishes. Another change in technology could revive it again. For example, when CPUs became much faster than memories, caches became important to speed up the slow memory. If new memory technology someday makes memories faster than CPUs, caches will vanish. And if a new CPU technology makes them faster than memories again, caches will reappear. In biology, extinction is forever, but in computer science, it is sometimes only for a few years. Consequence of impermanence is as follows. Text related to operating systems often looks at obsolete concepts. However, changes in technology may bring some of them back soon. For this reason, it is important to understand why a concept is obsolete and what changes in the environment might bring it back again. For example, early computers had hardwired instruction sets. The instructions were executed directly by hardware and could not be changed. Then came microprogramming, first introduced on a large-scale computer with the IBM 360, in which an underlying interpreter carried out the hardware instructions in software. Hardwired execution became obsolete. It was not flexible enough. Then RISC computers were invented, and microprogramming, that is, interpreted execution, became obsolete because direct execution was faster. Now we are seeing the resurgence of interpretation in the form of Java applets that are sent over the internet and interpreted upon arrival. Execution speed is not always critical because network delays are so great that they tend to dominate. Thus, the pendulum has already swung several cycles between direct execution and interpretation and may yet swing again in the future. This happens with large memory, protection hardware, disks, and virtual memory. Here is another example related to effect of large memory. The first mainframes had limited memory, for example, 128 kilobyte, mostly programmed in assembly language. Its operating system was written in assembly to save precious memory. Then compilers got good enough that assembly language was pronounced dead. But when the first commercial minicomputer was released, it had only 4096 18-bit words of memory. Assembly language made a surprise comeback. Eventually, minicomputers acquired more memory and high-level languages became prevalent on them. When microcomputers hit in the early 1980s, the first one had 4 kilobyte memories and assembly language programming rose from the dead. If we consider embedded computers, they often use the same CPU chips as the microcomputers. Some examples are 8080s, Z80s, and later we have 8086, and they were also programmed in assembler initially. Now their descendants, the personal computers, have lots of memory and are programmed in C, C++, Java, and other high-level languages. Smart cards are undergoing a similar development. Although beyond a certain size, the smart cards often have a Java interpreter execute Java programs interpretively, rather than having Java being compiled to the smart card's machine language. The same happens with protection hardware, disks, virtual memory, etc. The ideas invented in one context and later thrown out when the context changes, for example, assembly language programming, monoprogramming, single-level directories, etc., reappear in a different context, often a decade later. The basic operating system concepts on which operating systems are built are processes, memory management, input-output management, the file system, and security. In the coming chapters of this course, we will cover these concepts.